Yeah, so hello and welcome student for today's class. So this is our course MA425 Topology. Okay, and this is lecture number 11. Okay, now today we are going to learn something called the metric topology. Okay. Okay, so let me give an motivation towards this. So for example, in physical world, you know that for example, let me take a three-dimensional space R3, and in physical world there are two nice idea. One is given any point, any vectors. So any vectors, then we know there are two things. One is called the length of the vectors. Okay. And another thing is that the distance from two vectors. Suppose you have another vectors, then you can easily find out the distance, right? Okay, so this concept is a very important concept to find out lots of properties of the vectors and these vector spaces. Okay, the question is that do you have these kind of properties in general metric space? General topological space, or how do you, or rather how do you generalize these two ideas? So the idea of this length of vectors is actually generalized by something called norm, and you will learn this thing in function analysis. Okay, and idea of this distance. So this is length become generalization of length become norm, and then generalization of distance distance becomes metric. Okay, so so the metric you can think kind of a more general idea of distance. Okay, I mean in general in metric space we define this is generalization of distance, right? Now so how do you generalize this idea of distance in an arbitrary metric space? So let me define it first. So so you have a metric space, topological, maybe it's just a space. Okay, let X be a set, and then you want to check whether you have a metric or not. So how to define a metric? So a metric on X is a map from say X cross X cross X to R plus 0. Obviously 0 means it can be 0, or it can take value 0 also, union 0 is equal to 10. Okay, satisfying the following property. So okay, so what are the property I will write down? So satisfying the following properties. Okay, property number 1, what okay, yeah, so property number 1, what so this is a map, so let me write down the name. So maybe D from X to X2, that. And what are the properties? So D of XY, if you choose or maybe X1 X2, easy to remember. This D of X1 X2 is always non-negative. This is by definition, you can find out that in it. And D of X1 X2 equal to 0 if and only if X1 equal to X2. Okay, This is obviously the way I wrote the map. This property is obvious, right? So I don't have to write down. So it is better to write down d of x 0 if I not leave this. Number 2 is that this map has symmetric property. What does that mean? That means d of x1, x2. So distance from x1 to x2 and distance from x2 to x1 are same. So if you come to x2 to x1, the distance will be same. Okay. And the third but the most important property is called the triangle inequality, and that tells you that when you go from one point x1 to another point, this distance plus the distance from x2 to x3, another point, is always less than this is always greater than equal to the distance from first point to the third point. Okay. So what does that mean? That means you choose one point to another point, and though another point, this distance is always greater than equal to this. Okay, it can be equal when x2 will be lying on the line joining x1 and x3. Okay, this property is called the triangle inequality. Triangle property or inequality, anything okay. So if a map satisfies these properties, then we call this map is a metric. Okay, so this is kind of generalization of the distance in arbitrary arbitrary space. Okay, and the space x with such a map is called a metric space. So we say xd is a metric space. Okay. Okay, so now because we just have this metric, then we can define something called open balls, or some people call also epsilon balls. So how do you define open balls? So we define, say, let x belongs to x, and you define and obviously some positive epsilon. You define epsilon ball with respect to the metric D, center as x, and radius epsilon. This is the radius epsilon. So this is what this is kind of. You collect all such y such that the distance from x to y is bounded by epsilon, less than epsilon. Okay, clear? So what you do, you choose a point x, and you are checking how many such y's are there within this radius of alpha epsilon. Okay, and this is called the epsilon ball. So this is called epsilon ball. Okay, clear? And obviously you can choose any epsilon positive, doesn't matter. Now if you collect this epsilon ball, then what happens? You see that so let me collect this. So let this is collection of epsilon balls with respect to the metric D. X belongs to x and epsilon positive. Okay, now can you guess what kind of set is this? Now you see that this set has very nice property. First of all, this is a covering of open covering or other covering of x, right? So number one, you see that this is a open cover of x, obviously, as it for any x belongs to x, you just write down this, right? So x always belongs to this ball center as x, and you choose any epsilon positive. Okay, so what does that mean? That means this collection will cover all the element of x, right? It's obvious. And second property is that given any such epsilon balls, okay, and any element in the epsilon ball, you can find out another epsilon balls inside that given epsilon balls. And this is very important property which will prove you the second property of the basis. We will show that this actually forms a basis and of some topology, and then you can generate the topology, you know how to generate it. Okay, so so the second property, that property number 2, property number 2, that what is happening? So let you choose for example any open walls. So b d x y epsilon. Okay, so this is open wall, epsilon ball, and then you choose some elements y belongs to this epsilon wall. Then you can always choose another small open ball centered y, which is entirely inside this. Okay, so now let you just write down some epsilon 1 is see. So what does that mean? That means, so you have a point x, and you have kind of circle, right? Center at x. This is your x. Now you are choosing another point y, and then you're checking that what is this distance. So I just want to check that I can find out one more balls inside there, right? So my epsilon 1, so this is my total epsilon, and then I'm writing epsilon 1 is this distance. What is my epsilon 1? Epsilon minus distance between x and y. Okay, because y is sitting inside the epsilon ball center at x, so this distance between x and y is less than epsilon, so this is positive obviously, and hence you can talk about the epsilon balls center at y and radius epsilon 1. Okay, so this is the epsilon ball, the line, this inside one, and this is obviously a smaller ball with respect to the same metric, and this ball is actually sitting inside the original ball. Okay, so this is the important observation. Given any balls, you will have a point inside the ball, so you can always find out another small open balls inside that. Okay, this property will allow us to prove the second property of the basis, which says that given any two basis element such that the intersection of a point, then inside in that point, around that point, you can find out another basis element, right? So now number 2 property. So let so you choose say 2 balls. So let you have a point, for example, let me write down z, and that is sitting inside 2 open balls. So maybe let me write down the name, say, okay, so this is, or maybe y is enough, doesn't matter. So okay, so b x okay, so bx epsilon and b, so I'm not writing d always because this you understand, maybe epsilon dash. Okay, so what does that mean? Pictorially you have these and something like this. Okay, and then you see that z is inside this, so you can always find out one more ball that is always sitting inside both of them, right? Now how to write down these balls? So you write down these balls. So for first one, what you did, you can find out one ball, some epsilon 1, such that is b dz epsilon 1, which is actually sitting inside the first balls, bx epsilon. And for the second one, you can find out bd another epsilon, say 2, such that sitting inside b, say y epsilon, right? Epsilon dash. Okay. Now, if you choose the minimum of epsilon, epsilon 2, so let now you choose that epsilon 3 is minimum of this epsilon 1 and epsilon 2. Then what happened? Then this is minimum 1, and that is actually setting and set both. Then this be with respect to the metric D z epsilon 3. This is actually sitting inside the intersection of B D x epsilon intersection B D y epsilon dash. You understood? So what does that mean? That means that this collection has the property that if you have the intersection of two such elements, then there will be third element sitting inside that, right? So what does that mean? That means thus this forms a basis on X, right? And the topology generated by this, and we know how to define the topology generated by a basis. So you take all those open sets which are union, arbitrary union of this basis element, right? Or rather you can say the open set are those where inside that you have a basis element sitting. Okay, so the topology generated by these are called metric topology. Okay, so the topology tau which is generated by this kind of metric is called a metric topology. Metric topology on X. Clear? So the metric topology is what? The metric topology is actually coming from a metric. So you have a metric. The moment you have a metric, you can define the open balls, open sets. Those are actually basis element. And the moment you have a basis, you can generate the open sets. You collect all the sets which are open set, which contains a basis element, right? And obviously open. So a set is open if for any point belongs to the open set. That set there exists a basis element containing that. Okay, that is the meaning of open set. Okay. So this kind of topology we call a metric topology, and we say that the topology is induced by a matrix. Okay, maybe you can give some examples. So okay, so first example which is actually very popular, and that is coming from a matrix called a discrete matrix. So how to define? So X is anything given, and then you are sending a map from X cross X to that plus 0. Okay, and what is your matrix? So you choose any points x1, x2. So you have two choices, either 1 or 0, and if it is same, then it is 0. If it is different, then it's 1. So what does that mean? That means given any singleton points, these points must be an open point. That singletons are always open here, right? So these kind of matrices are called discrete matrix. Discrete metric, and it induces what kind of topology? It induces something called discrete topology. Okay, it induces the discrete topology on X. So this is clear that why singletons are all open sets, because given any singletons and given any another points which is different from that, so the distance is 1, right? So if you choose a epsilon ball with epsilon less than 1, then the epsilon ball containing that points itself. So every such singleton points are open open sets inside the basis element, right? Is that clear? Okay, and then obviously you can have another things called the standard metric. So what is standard metric on R? So you choose your x is real numbers R, okay, and you define the standard matrix. How you define standard matrix? So this is kind of the modulus of x1 minus x2, right, inside R. Sorry, modulus, okay, and you see that these will generate that's the standard matrix, okay. How these open balls look like here? So open balls at radius x, at a point x of radius epsilon. These are nothing but x minus epsilon to x plus epsilon, right? So this is clear. The standard matrices are also coming from. So standard topology, Euclidean topology is also coming from a matrix called standard matrix, right? Is that okay? So by now you can understood that some of the spaces are actually having this property that the matrix are actually coming from some underlying topology, okay, and these kind of topologies are very nice actually, okay. So for example, maybe I can define it. So this kind of space are called metrizable space, okay. So how do I, so a topological space is said to be metrizable if the topology induced by a metric, okay. For example, the discrete topology and the standard topology these are all metrizable, okay. That is metrizable, okay. And obviously you can ask that what are the conditions you require for that, and we need to learn something called countable axioms, separation axioms to learn this thing, okay. These are part of your syllabus, but maybe after midterm, okay. So and there is something called Euclidean Materialization theorem, so you are going to learn that thing after midterm. So right now let me just tell you that whenever you have a topology, you have some extra property also. That property was not there inside your original topological space without metric. For example, in original topological set, you know that open set, closed set, continuity, right? Open map. These are all these properties are all topological properties. But you may have some property which is not exist inside a topological space until it is metrizable. So if it is metrizable, you can define this kind of property, okay. And one such property is called a boundedness, okay. So this boundedness property you can define only for a metric space, so, or rather you can define for a topological space which is metrizable, okay. So how to define it? So because you have something more, so you can define something interesting thing which was not existing in general. So you start with that. So let x be a metrizable, that means it has a metric, okay, topological space okay, with the metric is D, with metric D is given, and then we define a subset A of x is said to be bounded if what happened, if this d of say a1 a2 is less than, so see if there exists some, obviously some real numbers, okay, so some positive real numbers, okay, such that this is M for all a1 a2 belongs to A, okay. If you choose for any such pairs of points a1 and a2 and check whether the distance between a1 and a2 is bounded by m or not, if it is possible for all such things, then we say that subset A is bounded. And this property, this boundedness property, is actually not there. It was not there inside a general topological space. Okay, clear? And obviously, the moment you have a boundedness property, then you can define something called the diameter. And this is again a metric property, diameter. It's not a topological property. Okay, so the diameter. So let a subset of X is bounded. Okay, and obviously I am checking non-empty also. Otherwise, is kind of backwards definition. Okay, and then we define the diameter of A is given by this formula. Okay, so I will write down DIMA, okay, for short. What will be this? This will be supremum or this distance A1 A2 and this A1 A2 are elements are A. What I am doing, so I am taking the this matrix A1 A2 and taking this distance between A1 and A2 for any arbitrary pairs of the elements of A, right? But you know that these points are real number, inside real number, okay? And because I already assumed that A is bounded, so this is a bounded subset of real number, right? And hence, because real number is complete, so its supremum exists, right? Every such thing has supremum. So LOB property will give you that this supremum exists, and we define this the diameter of A. Okay, and obviously one can ask that this diameter. Okay, so this diameter also depend on the topology, on the metric. If you change the metric, you can see that a set may have a different diameter with respect to different metric. Okay, for example, it can be one can find out a so suppose you know that this space is matrixable. Okay, then obviously with the help of that metric you can define a new matrix where every set becomes bounded. So that means every diameter of every set is finite, that you can find out. But in general, given a metric space, you don't know. For example, the standard matrix on R, that is matrixable, right? So you choose R and the standard matrix, this norm. So here you see that obviously you can define diameters, but you cannot say that every subset of R has finite diameter, right? Okay, but because of this metric property, I can change this matrix by another matrix, and then with respect to that matrix, it becomes a new matrix, which is a under which every subset of that space is bounded. Okay, so that means boundedness depend on the metric, not depend on the topology. But though I will change the matrix, it will generate the same topology. So it will not change the topology, just it will change the matrix. So this is an example of saying that there may be two matrices generate the same topology. Okay, and that I can show you later also. There are many such matrices which can generate the same topology. Okay, So maybe I just, you see that, so you have a matrix, say given matrix from on X, okay, and this is given to you, then you define R0, so define a new matrix that maybe say d bar, this bounded things, and d bar and defining from X cross X2 the same thing as so you choose 2 points and you write down this, the minimum of either distance from xy if it is less than 1 or 1. So the moment the distance from x and y is bigger than 1, you take that distance is 1, okay. And this kind of matrix, so obviously you can prove that this is a metric, right? So this is easy to prove that this is a metric, so maybe I will prove it, okay. And these kind of metrics are called standard bounded metrics. So these are called standard standard bounded metrics. Boundedness metrics, metric on X, okay. So I'm defining on X, that's why. So and this is induced by the matrix D, okay. So how to prove this d bar is also metric? So obviously first two properties are easily, right? Property 1 and property 2 are trivial, so you can easily check that this is 0 if and only x equal to y, and number 2 the symmetry property, right? This is also trivial, so it's just check it at home, okay. And number 3 you need to check, right? So number 3, what does that tells? That you need to check that given any xyz, then xy plus yz, this is less than or equal to xz, right? That you need to check the triangle inequality. Now how do you check? So there are two possibilities. So given 3 points xyz, so you check if the distance from xy less than 1 and distance from yz also less than 1, then what happen? Then obviously you know that then this will be equal to d bar of xy by definition, and this will be equal to d bar of this, right, by definition, right? Now because d is a metric, so we know that d of xz is less than or equal to d of xy plus d of yz, right? But because the first condition, what I assume they are less than 1, what I can say that this is less than or equal to d bar of xy plus d bar of yz, right? But what is the relationship between d and d bar? Now you see the d bar is minimum of that thing, right? So that means d bar, again you see that d bar of xz is less than or equal to d of d of xz, right? This is clear because d bar is defined by the minimum of either d bar x bar or 1. So it can be either equal or less than that. If d of xy is bigger than 1, then you choose d bar as 1, okay. And obviously that means this is from this equation it is clear that this is less than d of xy plus d of yz, right? So triangle is true if both the distance from x to y, y to z is less than 1. Now what happens if at least 1 is bigger than 1, I mean get equal to 1? Then also it is obvious, because if at least if this xy is equal to 1 or yz greater than equal to 1, and then what happens? Then obviously this is true, because d bar of xz cannot be more than 1, right? So this has to be then obviously less than or equal to either d bar of xz xy or d bar of yz. It's clear? Because left hand side cannot be more than 1, but right hand side you have at least 1 plus something, so it has to be bigger than that, right? Okay, so this shows that the way we define the minimum of d, x, y and 1, this forms again a matrix. This is called a standard bounded matrix. Okay, and under this matrix you see that every subset is bounded. So what does that mean? That means even though the original matrix of R is not bounded, now you have a new matrix become bounded, and you see that they both generate the same matrix. Why? Sorry, same topology. Why? Because the basis elements are same, right? So if you choose, you see that B, for example, these collections of B, D, X and epsilon. Okay, so I am choosing X belongs to, say, the space X, whatever the space, and epsilon less than 1. Okay, now this collection obviously is a basis for a topology, whatever the topology on X, right? And now you see that these collections and the collections these, that B bar X epsilon, obviously by the same epsilon less than 1, maybe this is a B dash of B bar. So they actually generate the same topology, because whenever you have a basis element there, you can choose a basis element there, and vice versa. So they generate the same topology, right? So the topology is same, but the same set may have a bounded and may have a diameter, like finite diameter or infinite diameter. That depends on the metric, which metric you are choosing. Okay, clear? So now we understood that the boundedness cannot be a topological property, because same topological space you have two different metrics, and with respect to that, for example, let me just give an example. So this is my R, and your A is for example, you choose anything, say natural number. Okay, now with respect to the usual topology, what is the diameter? Diameter of A equal to infinity with respect to Euclidean topology, right? Euclidean with respect to Euclidean topology, right? Euclidean topology is coming from that Euclidean metric. Okay, with respect to Euclidean topology, with the standard metric, I should not say Euclidean topology, I should say with respect to Euclidean metric. Euclidean metric. What is the Euclidean metric? So the distance d of the xy is mod of x minus y, right? But if you change that, that your d bar is the minimum of d and 1, then with respect to this d bar metric, what is the diameter of the natural number? Diameter of natural number inside R. Find out. This is homework. You see that this is bounded actually. Okay, so okay, so that will gives you that actually 1, so there's nothing to prove, so you just check it. So that tells you about that. You can actually make another matrix that tells you that gives you bounded property. Okay, so boundedness is not a topological property, though the topology is same. If you change the metric, something, the boundedness property will be also changed. This is the important thing we need to understand. Now, same thing we can do it for higher dimensional Euclidean space. So maybe it's a Cartesian product with in many spaces. Okay, same thing you can do it, and maybe I just want to define it, and then maybe we will finish it quickly. So if we have something, say Rn, okay, so which is Cartesian product with n many copies. N is a finite integer. Okay, so n copies. Then you can do the similar process. So here obviously you have the norm, and you know that how to define the matrix, the usual Euclidean matrix. That is nothing but square root of. Okay, so inside this, so you choose 2 points. So x, maybe say x1, xn, and y, maybe script. Okay, script y1, yn. Then what will the distance? Distance will be, the equivalent distance will be x1 minus y1 whole square, and blah blah blah, and xn minus yn whole square, right? And then take the square root. So this will generate, this is the equivalent distance which is coming from the this is the matrix which is coming from the norm also. There is a norm here, and then you can talk about the topology generated by, induced by the matrix. Okay, or you can do another matrix. So this is obviously Euclidean matrix. So let me write down Euclidean metric. Okay, but you can define another matrix, and in that metric, what you can do, you define, say, by row of xy, and what is row of xy, and what is this? This is, you choose the maximum among mod of xi minus yi, and I equal to, say, 1 to n. Okay, so that means you choose x1 minus y1, x2 minus y2, x3 minus y3, and whatever the maximum you choose, that is your distance. Okay, then obviously you can easily prove this is also distance. Okay, so you check that rho is also a metric, and is called what is the name? It named square matrix, actually. Square metric on Rn. Okay, so the square matrix, so what does that mean? So square matrix kind of, so first of all you have to understand how the open ball look like. Now you see the open balls are like Euclidean matrix. Open balls are what? Open balls are kind of a center at 0 is kind of this, right, circles of radius 1. But in square matrix, how open ball look like? So it's kind of square. Okay, so given a point, and you want to say what is that, say, let me write down a point x, maybe 1 to 1, so whatever you choose, and then what will be the open ball here with respect to the row? Add, say, x and 1 is that basis. So you just go the square, so the x is kind of inside the this epicenter, whatever. So this is the x. Okay, this is where the diagonals can intersect, and this distance 1 is 1. So what does that mean? That means this open balls is a square which center at x, and the sides are actually 2 units. Okay, this is open balls, and open balls at 1, this is kind of this. Okay, with respect to the Euclidean matrix. Clear? Now obviously one can now ask that which one is what is the relationship between these two topologies. which generated by the matrix, and the answer is they generate the same matrix, same topology, and that is nothing but the product topology. So product topology on Rn is generated by both the Euclidean metric and the square matrix. And why this two? Because you can easily find out that you check that this row distance between these, this is always actually bounded by this, okay, and this is also bounded by root n times rho of xy. This is obvious fact, because here you see, here you have only maximum term, here you have maximum term plus other terms, so this is bigger than that. But to check this one, this is also obvious. You check that the square of xy is nothing but x1 minus y1 whole square plus dot dot xn minus yn. There's some issue is going on. My laptop becomes very hot actually. Xn minus yn whole square, right? Now among these n many terms, one term will be maximums, and if you replace every term by the maximum terms, then what happens? Then this will be less than equal to n times that maximum terms, right? So that is nothing but the row. The maximum term will be nothing but the row square of xy, right? And hence this distance of xy, distance between x and y, is less than equal to root n times row of this distance, the square distance between xy. Okay, and that will tell you exactly. So from first equation, it is known that it is easy to check that this open ball contains inside this, and again this open ball contains inside this. So what does that mean? That means like these pictures, or if you choose this, you have these pictures. Okay, that contains a square contains inside the circle. So they generate the same topology that we already discussed once. Okay. Okay, so by this I will finish my today's talks. That the topologies on Rn, that is, which is nothing but product topology, the standard topology, they are coming from the Euclidean matrix and the standard matrix and the square matrix. And by the way, there are other matrices also. You can check. There are many other matrices maybe in between that, and they generate the same topology on Rn. Okay. Okay, so I will finish today's talks here.